Thank you for all staying here. And today, basically, we're going to the goodness of it of multi-class predictor. So basically, who am I? I'm a senior data statist in Trust AI. I have a PhD in applied math from the Technion. And I'm interested in data science, algorithm, math, and if you do feel anything interesting about that, if it's practical or non-practical, doesn't matter, as long as it's interesting, feel free to add me in your social networks, give me a call, send me an email, just do it. So basically, this is referring to Eagle Talk, and basically you want to all of us have lunch in a few minutes, and unfortunately I'm going to stuck you in for 15 more minutes. So basically, why are we interested in multi-class prediction? All of us are doing a binary prediction, and so why bother? So basically, it comes from lots of different applications. The first application is the e-commerce. If you want to buy in a website a few items, and it doesn't make any sense to combine them. Like if you want to buy a shirt, pants, and shoes, those are different items and they should not be in the same class. The second motivation, it's come from the co-author of this work is Nathan Katz. He's working for Checkpoint and he's interested in cyber and classifying all the cyber attack as malware and non-malware. Doesn't make much sense because some of the attacks are extremely different than the others. So trying to detect them in one class would cause more false positive than true positive. And the third one is another issue what my motivation was is the IoT. I was giving consulting work a few years, actually it was almost 2 years ago, for a company that want to classify which kind of grains are grounded. It can be coffee, it can be nuts, it can be corn, and all those grains were very different, and they had no idea how to classify them. So when I got to as a consultant, and at first my thought, it's obvious. It's probably you can find it in the web or something, and it turned out it doesn't. Like all the solution people suggest, and we'll go over them in a few minutes, were not. I didn't feel good about them. They had a feeling that are not satisfying, and this is one of the reasons that I was hired. So I gave them some kind of solution. Later on, I think I gave a better solution, and you're going to see the better solution. Another aspect that you can see is predictive maintenance. Let's say you're running a hospital, and you're detecting the wrong defect in some kind of your gear, and you bring the wrong technician. It's not a pleasant thing. So you do have those multi-class, although most people in the data science somehow doesn't talk about it. This problem exists, and you should be aware of that. And why do we care? Okay, I think each one that's been in Shir's talk can answer. The first one is fairness. And I think she stated that way better than I can do, is that if you spotting something which is not fair in not only a binary, but in the multi-class, it can be very important. The second thing is that in the financial firm, it's very finding weak segments. Some of the segments are getting better classified, some worse, and you got to take this into account. And of course, things should be more robust, and doing the finding weak segment and understanding that your classifier is good not only for the main class, but for all the classes is very important for robustness. And if you're interested in adversarial examples and finding those classes that for some reason your classifier disperse, it would give you a huge advantage. So let's revert the plain reasons, is the one against all. One against all is basically the most naive. You take one class and you see how it's against the all, and then you do it all. Is this a pants? Is this a shoes? Is this a shirt? And so on. This is a very exhaustive method, and in many cases you're missing lots of interesting. Another way is that taking all the pairs and kind of combining all the pairs. It has some problem of its own. It's useful, but you can do it. And another aspect, if you have domain knowledge, is you cluster. You think, okay, let's consider classes together. Let's combine classes, and if you're in the major class, and then do another. But this sounds very promising. But as all of you are data scientists, and you know that usually your knowledge of the domain is not as good as you wish it was, so I don't know how to do that, if anyone. The second thing is embedding. Embedding is a very nice technique. Basically what we're doing, we're kind of embedding all the classes to some kind of a latent space. In this latent space, we do some kind of regression, and this is regression, everybody's happy. The main drawback of this method that doing this latent space embedding is a hard job. So some people are doing it with nets, but it's not easy. So let's start it with the binary case, and then we'll go back to the multi-classes. So binary cases is you have positive and negative, and beware, the class is in balance. So this case can be even more problematic in many cases. So what do we know? We know that accuracy, which is the prediction, the percentage of being right. Recall is the percentage of being right given that you were predictive positive. Precision is being right given you are real positive. Specificity, predictive negative, you're right. And NPV, negative predicted value, for some reason this quantity doesn't get good PRs. Nobody likes it for some reason. And it's you're real negative. And now let's go for things that all of us know. Back in high school, we learned about the algebraic mean and the geometrical means. And here's the F1 score. The F1 score is basically just the harmonic mean of the recall and the precision. If you're using scikit-learn, you can use it in the NPV and the specificity. It's called F10, F10. And from this example, anyone know why we are using the F1 score is so popular? The reason is the harmonic mean is dominated by both the algebraic and the geometric. So you get the most conservative quantity, which is usually what you desired for. And the Mathews correlation. Mathew still is a biochemist, and this is just taking the geometric mean of those quantities, and he's taking the determinant of these metrics. And why are we taking determinant? Determinant is the area of the paragram that is spanned by the vector of the matrix. So basically, if you want to take home message, each time you see a determinant, think about area, volume, stuff like that. Another interpretation of the Mathews is the Pearson correlation between the predicted vector and the real vector. So this combine. So let's go back to the multi. So basically what we need the class renaming. Why do we need the class renaming? Because just like in graph, the classes might differ and people might change, and we don't know which classes are more important and less important. And if you have plenty of classes, you need to do invariant for that. The second thing is just the equivalent to a non-biased estimator, is that if you're flipping the target and the predicted, you want to be no change. And obviously you're bounded by 1, and if you're doing perfect, perfect, it's got to be 1. And we have here a confusion matrix as well. Okay, and another quantity, it doesn't matter the entire, but the thing is that we are asking how much things are correlated. Just let's say, what does it mean? If I'm being, let's say, a male and in his 40s is just like the percentage of being a male times the percentage of being in his 40s. So basically this is important. So basically we get here the Kramer C. Each one of you which is which not using it is an EDA process. It's about time to start using this quantity for categorical values. So, and basically, so how can we use that? We can use that, use a correlation saying a vector, if you got predicted to class C and you are in class D. So basically you can use the same correlation here and getting some kind of it's not a perfect, it has some drawback, but it's a good start. Basically, the second thing that we did is that we used the trick about the Mathews. We used the same matrix, and we took the matrix, and we took. Why do we get? While using determinant? Determinant is a hypervolume in 3 dimensions it's the volume, in 4 dimensions it's hypervolume. Forgive me that I'm a little bit lacking drawing things in 4 dimension. My bad. So basically it's a good, so let's sum it up. Basically we can use Kramer, you can use generalized. There's some other method which is kind of equivalent to those, and so basically what we achieve in this talk, we achieve that if we have multiclass, we can give quantity that would tell us the goodness or the badness of the fit, and this is about it. So basically we introduced a classifier for goodness of classifier. Next time you see kind of modifier, you can use it. I think getting the geometric interpretation is very important. Like for me, if I don't understand the geometry and what's going on behind the algebra, it means that I didn't fully understand it, and I encourage you to do the same, because after you do that, you realize that things make sense or doesn't make sense. If things doesn't make sense, I think Igal gave a very good talk and mentioned what happened when things are emerging from the data but doesn't make any sense, and you get lots of bizarre stuff. And understanding geometry would give you a better way to avoid that. And anyway, so basically, if you find this talk interesting, or do you want to contact me for any other issue, feel free. In Facebook, LinkedIn, Twitter. I'm not that active in Twitter, but you can try and you can mail me. And I have 1 minute, so I'll tell you about Trust AI. Trust AI is the startup we're working. We're doing in machine learning omitting. So basically what we're doing, we're tracking all those nonsense things that the data might occur, either fairness or mistakes or wrong classifier, and this is what we're doing. If any one of your firm is interested in that and you want to learn more about it, feel free. Thank you very much.